Integration in two variables. Our goal is to introduce the iterated integrals for multivariable function. We're going to talk about the Riemann sum and extend and generalize the idea to functions in two variables, three variables, and so on. The integral of a function of two variables, f of x and y, is called the double integral, and it's denoted by, as you can see, we're going to use two integral symbols over region D of the function f of x and y, dA. This dA represents dx, dy, or dy dx, depending on how you are completing the integral. So basically, trying to find the volume or the joint probability or other concept that you learned in calculus. You had integral, now you're working with double integral. So our goal is basically divide up the base in xy plane into smaller rectangles and then calculate the height, which is going to be on the function f of x and y. Add all of those little volumes together and calculate the volume below here. As you remember in calculus, elementary calculus, we had an interval a to b, and then we divide up that interval into smaller sub-intervals, delta x. And we called it a regular partition. Suppose a and b is a closed interval containing n sub-intervals, x sub 0 to x sub 1, x sub 1 to x sub 2, and x sub n minus 1 to xn. So these are these little sub-intervals, as you can see here. They have equal length, which we denote by delta x, b minus a, divided by n. A is x sub 0, and b, the endpoint, is x sub n. Each endpoints x sub 0, x sub 1, x sub 2, x sub n minus 1, and x sub n of the subintervals are called grid points, and they create a regular partition of the interval a to b. In this case, the kth grid point is x sub k, which is a plus k times delta x. In the kth subinterval, x sub k minus 1 to xk, we choose any point, x sub k star, and build a rectangle whose height is f of x sub k star. The value of f at x sub k star is denoted by f of x sub k star. The area of the rectangle on the kth subinterval is the height times the base. The height is f of x sub k star times delta x. So we basically have the graph of the function. On the horizontal axis, on x-axis, we have our partition. Then we find the height. We multiply each height by the length and calculate these areas. Adding all of these areas together give us the Riemann sum, which is a good approximation for the area below the curve. Eventually, as you remember, we take the limit of the Riemann sum as delta goes to 0, and we define the definite integral of f of x dx, x ranges between a to b. Now we take this idea and define the double integral. If you have a function z equals to f of x and y, well, the base is on xy plane, and we're going to divide this up, partition this into small rectangles. delta A sub k is delta x sub k times delta y sub k, which is the area of these small rectangular objects. Now, if you find the height of the k box, which is f of x sub k star, y sub k star, and multiply that by this little area, you basically find the volume of the kth box. Now, if you add all of these together, you basically have the approximation of the volume. The double integrals. A function f defined on a rectangular region R in the xy plane is integrable on R if the limit of the Riemann sum of f of x sub k star, y sub k star, delta A sub k exists for all partitions. This guy basically represents two Riemann sums. And when you're taking the limit, as delta goes to 0, you have the double integral of function f over R. As we saw examples for elementary calculus, calculating the area using the Riemann sum, we have the exact same thing for the volume. In this question, we are interested in estimating the volume of a solid that lies above the square R, which is the Cartesian product between closed interval 0 and 2 by closed interval 0 and 2. So here you have the closed interval 0 to 2 and the closed interval 0 to 2. The Cartesian product gives you this small rectangular region. On top of it, you have elliptic paraboloid z, which is 16 minus x squared minus 2y squared. The question asks us to divide R into 4 equal squares and choose the sample point to be the upper right corner of each square R sub ij. So the squares are shown in the figure. Again, we are taking this little base. And as the question said, we're going to divide this up into 4 equal squares. Perfect. The first square, the second square, the third, and the fourth. And it says, hey, the sample point needs to be upper right corner. Upper right corner for the first square is 1 and 1. For this square is 1 and 2. For this square is 2 and 2. For this square is 2 and 1. And we have the graph of the paraboloid here, which shows the ceiling of this object. The area of each square is delta A equals to 1. Why is that? Because the length here is 1 unit. The length here is 1 unit as well. So we can basically see 1 times 1 is equal to 1. Now, the volume is the double summation of f of x sub I, y sub j, delta A. J starts from 1, goes to 2. I starts from 1 and goes to 2. I represents x values and j represents y values. Take a look. Here you have your grids for this small rectangular base that you have here. We divided that into 4 equal squares. We call the first area R sub 1 and 1 using the same upper corner on the right-hand side, which is your sample point, R sub 1 and 2, 1 and 2, R sub 2 and 2, which is connected to 2 and 2, and R sub 2 and 1, which is presenting the area for the sample point. Now let us begin calculating. This is equal to f of 1 and 1 delta A. So when I is equal to 1, j equals to 1, you get f of x sub 1, y sub 1. F of x sub 1, y sub 1 is 1 and 1. So you plug that in here, times delta A. This is equal to 13 times 1. Why 13? When you plug in 1 here into the function, f of 1 and 1 is 16 minus 1 minus 2, which is 13. So this is the very first volume. Now for the second volume, we're going to calculate the height, which is f of 1 and 2 times delta A, which is basically calculating the volume over R1 and 2, which is equal to 7 times 1. When you plug in 1 and 2 into the function, you get 7, and delta A is fixed. It is equal to 1. You can continue this process. Calculate the next volume, f of 2 and 1 times delta A, which is 10 times 1, plus f of 2 and 2 times delta A, which is 4 times 1. The approximation is 34. So the volume of the object below this elliptic paraboloid bounded to this base is about 34. So this is an old-fashioned method calculating the volume. For integrable functions, you can easily use the shortcut that you learned in elementary calculus and do the calculation much more easier and faster.